All right, today we're tackling problem 1.23 from a real classic in the physics world. Yay, Irodov's Problems in General Physics. This is one of those fantastic problems that really makes you understand how to handle motion when acceleration isn't constant. So let's just dive right into the challenge, shall we? So here's the problem statement. We've got a particle, and its deceleration, w, is equal to some constant a times the square root of its velocity. Now, if you're wondering about that word modulus in the problem, don't worry. It just means we're given the magnitude of the deceleration. The real curveball here is that the deceleration isn't just a fixed number. Nope, it changes as the particle slows down. Our mission then is to figure out two things. First, what's the total distance it travels before it finally stops? And second, how long does that whole process take? Okay, so what do we do here? Well, those standard high school kinematics equations, the ones like V equals U plus AT, yeah, we can't use those. They're completely off the table. Why? Because they only work if your acceleration is constant. But ours isn't. It actually changes as the velocity changes, which is something you see all the time in the real world with things like air resistance. So we've got to go back to basics, back to the fundamental definitions. And you know what that means? It's time to bring out the language of physics, calculus. Now, this is really the key to the whole thing. Think of this slide as our toolkit. These two equations come straight from the definitions of velocity and acceleration. On the left, we've got a equals dv dt. Let's call this our time tool. See how it connects acceleration directly to a change in velocity over time? Then on the right, we have w equals v times dv ds. This is our distance tool, and it links acceleration to a change in velocity over distance. Honestly, the secret to cracking this problem efficiently is just picking the right tool for the right job. Okay, let's gear up for our first quest, finding the total time it takes for the particle to grind to a halt. So looking at our toolkit, which one are we going to grab? If you're thinking the time tool, w equals dv dt, you are absolutely spot on. Let's put that thing to work. All right, so the key here is just breaking this down into 4 really clear steps. First up, we set up the equation. We grab our tool, dv by dt, and we set it equal to the deceleration from the problem, which is negative a times the square root of v. And that minus sign, that's super important because we're talking about deceleration. It's fighting against the velocity. Okay, step 2, we separate the variables. This is just a bit of algebra, really. We get all the v stuff on one side and the t stuff on the other. It just preps the equation for integration. Step 3 is my favorite part, because this is where we tell the story of the particle's motion with our integral limits. Velocity starts at v0 and it ends at 0, right? It stops. And time, it starts at 0 and goes all the way to some final time t, which is exactly what we're trying to find. And finally, step 4, we solve the integrals. And that's going to give us the direct relationship we're looking for. Fantastic! We've got the time figured out. Now it's on to our second quest, finding the total distance traveled. So let's look back at our toolkit. Which one are we picking this time? It's got to be the distance tool, right? Of course. Let's use w equals v times dv over ds. And this is what's so brilliant about having a solid method. We just follow the exact same 4 steps. Step 1, set up the equation with our distance tool. So now we have v times dv ds equals negative a root v. Step 2, separate the variables. A little bit of algebra, we get all the v terms on the left and the s terms on the right. Easy enough. Step 3, define the limits. The story here is pretty similar. Velocity still goes from v0 down to 0, but this time, distance goes from its starting point, 0, to its final stopping distance, which we're calling s. And then step 4, we solve the integral, and boom, out pops our answer for the total distance. And just like that, with both integrals solved, we've done it. We have officially cracked this Irodov problem. So let's take a look at our final answers. So from that second quest, we found that the total distance, s, is 2/3 of the initial velocity to the power of 3/2, all divided by that constant a. We should always ask ourselves, does this make sense physically? And yeah, it absolutely does. If the initial velocity is higher, it travels further. Makes sense. If that deceleration factor a is stronger, it stops in a shorter distance. Perfect. And from our very first quest, we find that the time t it takes to stop is 2 times the square root of the initial velocity divided by a. And again, let's do a quick sanity check. A faster start? Yeah, it should take longer to stop. A stronger deceleration? Well, it should stop quicker. The physics checks out beautifully. So what's the big idea here? What should you really take away from all this? Look, it's not about memorizing these specific formulas for this one problem. The real lesson, the powerful lesson, is the method.
When acceleration isn't constant, you have to go back to the calculus definitions. You have to pick the right tool for the job, one for time, one for distance. And the most critical skill of all is translating the words of the problem into that first differential equation. If you can get that right, the rest is really just following the steps.
And to leave you with a final thought, just think about this. What if the deceleration law was totally different? Let's say it was proportional to the velocity squared, so w equals k times v squared. How would our method change? Well, the beautiful answer is it barely would. You'd still pick the same tool, you'd still follow the same 4 steps. The only thing that would change is the function you have to integrate. And that right there is the power of understanding the fundamental method. It doesn't just solve one problem, it unlocks an entire class of them.